Math 1314, Tyler Junior College, Section 3.5, Rational Functions, Slant Asymptotes. Disclosure, in some textbooks and in some professors' opinions, or perspectives I should say, slant asymptotes are also referred to as oblique asymptotes. I've even seen them called skew asymptotes, although I think that terminology is a little outdated these days. So what do I mean by slant asymptotes? Well, not all asymptotes are horizontal or vertical. Some asymptotes can be slanted. In other words, you can have an asymptote that's a little bit more diagonal-like. So the question is, when can we expect this? And when we expect it, how do we locate it? Here's the answers to both questions. If f of x equals p of x over q of x, so you have a rational function, and here's the criteria. The degree of the numerator is 1 more than the degree of the denominator. Let me say that again. The degree of the numerator is 1 more than the degree of the denominator, like this one. The degree of the numerator is 1 more than the degree of the denominator. Then, y equals the quotient of this polynomial division problem is a slant asymptote. So locating them, or identifying when they occur is easy. Locating them depends upon doing a division problem. In this example, f of x equals x squared minus 3x minus 4 over x minus 1. Notice that the degree of the numerator, which is 2, is 1 more than the degree of the denominator. Because of that relationship between the degrees, this will have a slant asymptote. To locate it, we have to perform the division problem. Now, you can use long division, but this is tailor-made for synthetic division, or rather, synthetic division is tailor-made for this problem. If you don't know how to do synthetic division, or you've forgotten, please go watch the video series for section 3.3. All right, so the box number will be 1 because it's the opposite of the number in the divisor. The top row is the coefficients of the dividend, so 1, -3, -4. This will be a quick synthetic division. Bring down the 1, multiply by the box. 1 times 1 is 1. Add to get -2, multiply by the box. 1 times -2 is -2. Add to get -6. So this means that our function, our division problem, is equal to the bottom row are the coefficients of the quotient, but it starts 1 degree lower. Since the dividend was a second degree polynomial, the quotient is a first degree polynomial. So this starts with x to the first. 1x to the first minus 2. And then the last number is your remainder, plus -6 over x minus 1. So this means that this function is equal to this one, but more importantly, it exposes the equation of the slant asymptote. The slant asymptote is y equals that. I'm going to put SA for slant asymptote, y equals x minus 2. The reason it's the quotient is, remember the role of a horizontal asymptote is to dictate the behavior when x approaches infinity. If x approaches infinity, this fraction collapses to 0 because the denominator grows while the numerator is static, meaning that as we get larger and larger, our graph gets closer and closer to that function, so that line. In the next video, we're actually going to graph this function, and when it comes time to analyzing the asymptotes, we will pause and mention that this had a slant asymptote, and it was y equals x minus 2. Now, heads up for those of you that are going to go further down the math path. For those of you ending in college algebra, you can stop the video now because you're curious. I'm not going to do the final video I plan to in this series, but I will allude to it briefly. There are asymptotes that are not lines. You can have parabolic asymptotes, parabolas, or any graph can serve as an asymptote for another. The time you get a non-linear asymptote is when the degree of the numerator is even greater than 1 more than this. So for example, if we had f of x equals x cubed over x minus 1, this would have a parabolic asymptote, a parabola. How do I know? And this is rarely ever discussed in any math classes. I've never been taught this. I just observed it and said, hey, this is a nice follow-up. If the degree at the top is greater than the degree at the bottom, then there will be at least a slant asymptote. But the bigger the difference, the bigger the degree of the asymptote. Specifically, the difference of the degrees is the degree of the asymptote. And since this is a third degree over a first degree, the difference is 2. This would have a second degree. This would have a second degree asymptote. So a parabola, because the graph of the second degree polynomial function is a parabola. And even more so, to locate that parabolic asymptote, you would just do the division. Now, we can do synthetic division with this. The box number would still be 1. The top row would be 1, 0, 0, 0, because it's missing every term except the x cubed. So if we just ran our way through the synthetic division, then the quotient would be x squared plus x plus 1, and y equals this parabola would serve as a parabolic asymptote. So in the middle, it might not reach the asymptote, but as it goes out towards the ends, it's going to get closer and closer to that parabola. So if you're really interested, I invite you to get the graphing technology of your choice, make up a rational function with a larger degree in the numerator than denominator, perform the polynomial division, and whatever your quotient is, graph that, and you'll see the ends of the original graph getting closer and closer to the ends of the asymptotic graph. I wonder if you're regretting watching the end of this video now. That's okay. If even one person benefits from that discussion, my mission is accomplished.